I'm going over the electronics parts I'm going to use within this demonstration. All these parts are available locally very easily if you wish to duplicate them from Amazon, Radio Shack, eBay, Automation Direct, and you probably have local suppliers in your local areas. Could be just about anywhere to find these. Now what I have here, I'm going to start out with 3 1000 ohm resistors, and being I'm using a breadboard, I'm using half watt resistors which plug in to the breadboard very easily. I have 2 330 ohm resistors, again 1/2 watt, and I also have a 1 kilo ohm resistor, 1000 ohms, and 3300s or 3.3 kilo ohms. I'm also using 2 light emitting diodes. Could be any color. The ones I'm using are 3 to 6 volt. We have a standard silicone control rectifier, and we have 2 different transistors. One is NPN, one is PNP. Now, breadboard right there is an 830 hole breadboard. They make them smaller but not much bigger. But all these connect right there. Every one of these lines will connect straight up and down. There is no side-to-side connection. So you create your own side-to-side connections. The power strip up here will connect right across. And each one of these groups of 5 terminals are going to be isolated from all the other terminals. So it's kind of easy to understand once you use them. I'm also going to use in this demo, I might use some standard alligator clip jumpers. Where I have some momentary contact push buttons. We have a 24 volt light, a standard incandescent light, and I have a 1000 ohm potentiometer. So it's a variable resistor. Okay, 1000 ohms. I'm also going to be hooking everything up with 24 gauge solid wire. Now the transistors, we look in these, they're kind of small little devices and they're hard to read unless you hold them right there in the sunlight just perfectly. Then you can actually read the numbers on the face. But they do make meters that'll test these. Now how this works is we got a standard power transistor or switching transistor, 2N222A, which is negative, positive, negative. We're going to get into these terms here shortly. Now the leads on the transistor, the center lead will always be the base. As you face the flat side of the transistor, the lead on the right will be the collector and the lead on the left will be the emitter. How the transistor actually works, we're going to get into that in detail. We're also using a PNP transistor, 2N2907A. Okay, same thing, different numbers, but again the base circuit is going to be in the middle. The emitter's on the left, the collector's on the right. So we have to understand and know what those leads are and how all these leads work. So we have to get into the basic theory of operation. We also have here what's going to be a silicone control rectifier, referred to as an SCR. Now again, the number is going to be kind of hard to read right here based on the lighting. I took the picture in. But on this SCR, the lead on the left is always going to be what's called A1, the center lead is A2, and the lead on the right will always be referred to as the gate. Now how this works is very similar to a diode, but it's a diode with a switch. And again, we learn the basic operation. I'm going to be using 2 light emitting diodes. Now we could use virtually any color we want. I'm using just a white and a yellow. Now the LEDs, we look on the drawings, you see this symbol everywhere, which is a diode with the 2 arrows coming off of it. That's light emitting diode. You have a negative side, you have a positive side. Negative side is the cathode, positive side is the anode. Now the LED is just a diode. That's all it is. But when current passes through, it gives off light. Now, if we look on the leads are going to be different sizes. The shorter lead is always going to be the cathode, which is negative. The longer lead is going to be the anode, which is positive. So we can identify them right off the box, right out of the package. Negative to positive. Now, how this is going to work is this diode will allow current to flow through the diode from the negative side to the positive side. So we do have to understand how these things will work. Now, I'm also going to use diodes, a standard diode. There's different sizes and shapes. These are two standard 600 volt diodes with a breakover of 1 amp. Well, which means they'll fry basically over 1 amp. Now, the side on that diode that has the stripe onto it, this is going to be the cathode, the side with the stripe. The side without the stripe is going to be the anode. So that current going through that diode will go in that little area that has the line and come out the anode. So in the cathode, out the anode. Now keep in mind, diodes can be from these little small components here to very large. Every one of these will work the same exact way. Now another common diode you see within industry is what's called a full wave bridge rectifier. We'll get into how this works and what it is. It's not complicated, but it's identified right here on the front where the AC terminals are, and this is identified by the sine wave, that little waveform. So these two terminals opposite each other, they're going to be the power coming in AC. One terminal, or the flat side, will be identified with a positive. The opposite terminal will be the negative. Okay, so again, it's not hard to understand how they work. It's a very simple process. We're going to get into detail on how diodes work. Now, resistors themselves, these resistors are going to be identified by color bands. Some resistors are going to have 4 color bands like the ones I'm showing on the picture, and some are going to have 5. The color bands right there, the colors themselves are associated with the numbers. There's always going to be a common list. So color bands 1 to 3 are going to be valued. Black is 0, brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, violet 7, gray is 8, white is 9. Okay, so these are going to be the bands. But now, if there is only 3 bands on, or 4 bands on that diode, right here we got the 4 bands, which means right there, this third band right there on this group of resistors, not diodes, resistors, this last band right there will be what's called a multiplier. If there's 5 bands, it'll be the 4th band that will be the multiplier. Okay, so the multiplier itself is simple. We take this first one on the top identified. We have a brown, which is the value of 1. Next is the value of 0. And the red is 2. Okay, the red right there is the number 2, which is 100 ohms. So what we have right there is 10 times 100. So this would be a 1000 ohm resistor. 10 times 100. The last band right there is going to be a colored band. It's going to be gold or silver usually. Gold or silver. The common points on gold and silver on the last band is a tolerance. The tolerance itself could be 5% or 10%. Now, if there are other colors on that, then that band, that tolerance will be less than 5%. So there are different colors for these bands. So we can identify each one of these. This one resistor, which is orange, we have 3, 3, then we have a brown. which is times 10. 33 times 10, 330 ohms. So 330 ohms on these two resistors with a 10% tolerance or 5% tolerance. So that will be within 5% of that 330 ohms. So it's not hard to identify, but it does take some getting used to. Now some of these components can be kind of small and hard to identify colors. So plan B is always measure it with an ohm meter. Diodes, a simple breakdown of operation. We have two different terminals here. You have a cathode, you have an anode. The symbol for a diode, you'll see this on everything from electronics to motor controls to high current devices. It's all throughout industry and they're all different shapes and sizes. Cathode, anode. Cathode is a negative polarity, anode is a positive polarity. The electrical current will only pass through that diode in one direction, from negative to positive. So it passes current through one way and it blocks current the other way. What that actually means is, if we apply an AC signal to the cathode of that diode, what goes through the diode, or what comes out of the diode, is only 1/2 of that sine wave. So this diode does what's called, it rectifies. It is a rectifier. It only allows current to pass one direction. Now the diodes themselves, and we'll get into this, we'll build this circuit, we apply a power, we take a measurement with an oscilloscope right here, and we see the sine wave coming in. But we take a measurement with an oscilloscope right there on the back side of that diode on the anode, and we see what's coming out. So the current right itself is rectified. It only allows current to flow through one direction. Now if I were to go ahead and install a push button across that to bypass the diode, well, one, when that button is open, this light is on, but it's dim. But when I push the button down, that's when that full sine wave comes back in, and it's bypassed, and the load gets full voltage much brighter. So I will demonstrate how this works. What I'm showing here is a standard diode set up on a little breadboard. What I have right here is power coming in, AC power coming in. We have a neutral, we have a hot. We have a jumper taking the power source to one side of the diode. The other side of the diode is connected to a simple indicator light. Passing through the light, the power now goes out back to neutral. So I'm using 10 volts of power. Now I go ahead and turn this on right there, and notice right there we all got the light that's on, but it's not exactly the brightest, but it is on. We do have power. Now if I use my oscilloscope, what I'm going to do with my oscilloscope is I'm going to apply one lead to one side of that diode, and I'm going to apply the other lead to the other side of the diode. And we're going to look on the oscilloscope to see exactly both sides of the waveforms. Now I'm going to do another. I'm going to go ahead and take these test leads off of the board. And I'm going to bypass this diode. Turn off my power source. What I'm going to do is I'm going to bypass this diode with a momentary push button. Momentary push button. So I have a little push button right here. We turn the power back on. The diode's on, the power's on. But if I push that button down, notice right there the light gets brighter. All I do is push the button, the light gets brighter. If I bypass that diode, now the light sees the entire sine wave rather than half the sine wave. If I let go of the button, that light is on, but it's only registering half the sine wave. And I bypass the diode with this switch, it now sees the entire sine wave. Now the LED operates identical to the average diode. The only difference is as current passes through, it gives off light. Okay, so we have AC power coming in. We have half the AC power coming out. And again, if I were to put a push button straight across this diode, when I push the button on, we get the full AC sine wave once I push that button down. And what happens is this diode no longer gives off light. It's shorted out. And when I release the button, well, the diode turns back on, the LED turns back on, the light turns on behind it at half the brightness. What I did here is I added a 330 ohm resistor and I replaced the diode with a light emitting diode. This can be a yellow light emitting diode, so yellow is the color. I turn on the power, the LED goes on. I push the button down, well, my light's on, but barely. I push the button down, and now my indicator light's on. So the point being is, as long as there's current flowing through that diode, it turns on. The LED is a diode, not just identical to the first one. The only difference is when there's current going through it, it emits light. Now, because I'm using a 3-volt LED, I had to put a resistor in front of it to create a voltage drop, so I do not actually destroy my light, destroy my LED. So the resistor has a purpose at this point. Now, another type of rectifier is what's called a bridge rectifier. What this is going to do is it's going to allow the passing of both sides of the sine wave. So I apply AC power right here to both diodes. One diode is forward, one diode is reverse. Well, one diode blocks current one direction, one diode blocks current the other direction. The resulting output of these diodes is you have what's called a pulsating DC power. This puts both sides of the sine wave on the same side of the sine wave. So there's no longer a positive and negative waveform. This is referred to as pulsating DC. You see a lot of this in industry, in small equipment, large equipment. It's everywhere. Small diodes to huge diodes. But you're coming out with one of these types of waveforms. Now, once you get this type of waveform, You can run DC on it, anything, but then again, this ripple effect right here does cause problems. So this is where a capacitor is then used. And the capacitor filters that out to a straight line. What I did here is I replaced the one diode. I replaced the LED with two diodes. One diode one direction, one diode the opposite direction, and this creates what's called a bridge rectifier. Not a high current rectifier, but a simple rectifier that allows me to use this with DC. Now, what I have here now, if I push this switch down, the push button, it doesn't do a whole lot of good for anything. It is a small change in power, but not a whole lot. This is because both sides of the sine wave are now on one side of the rectifier. Now, how this is going to work is I'm going to go ahead and take my oscilloscope, and I'm going to put one lead of the oscilloscope to the power circuit coming in. So this would be the AC sine wave. And with the other lead of the oscilloscope, I put the lead on the power coming out of the diodes. And we're going to see that on one side we have an AC sine wave, the other side we have pulsating DC. The full wave bridge rectifier is going to take AC power going through its input. So connected the hot and the neutral, that AC power on the top half of the sine wave is going to flow through the diode, pass from the diode, through the load, back through the next diode, back right there, back to neutral. So that's one half of the sine wave. On the second half of the sine wave, current flows backwards. So that current is going to flow back in from the neutral side, back through the diode, back through the actual load, and then back to the hot. So what we have going through that diode, through this load, you're going to have AC power passing one direction. This is known as pulsating DC power. Pulsating DC. If I use just a full wave bridge, this circuit might only be good for 1 amp of current. But if I go ahead and use a full wave bridge, this circuit is good for about 5 amps of current. So that full wave bridge rectifier does the same thing as a bridge rectifier. But this allows a higher current device. So it's this type of device that's actually used more often. What I've done here is I've installed 4 individual diodes to make a full wave bridge. Power comes in AC right here, passes to this section of the diodes. We have the cathode connected to the anode. That power right there passes for the first diode through the cathode, through the lead, through the light, back to the next set of diodes, where it passes through the cathode, back to neutral. Now on the second half of the sine wave, that power is coming in from neutral, passes through this diode here, back to the lead, to the light, passes from the light, back down here to this point, and then back to the hot. So we have a circuit right there that's a complete circuit. So if I turn that on, we have light. Now, if I was to add to this my oscilloscope, I'm going to attach the oscilloscope to the section of power going in. All I got to do is get onto one lead, and I have AC power. And if I put that oscilloscope lead to the second section, the lead coming out, we have DC power, pulsating DC. But I can do this to either one of these legs, and I'm going to see pulsating DC power. So coming through this light, we're always going to see that pulsating DC. What you see now is a simple, right there, full wave bridge rectifier. Typically it's going to be a little disc or a big square with leads coming out of it, or it could be 4 individual diodes. Now I have AC coming in to 2 sides, to one side on this side, one side on this side. That's my hot and my neutral. I'm using 10 volts. Then from there, the 2 outputs, power from this side of the output and this side of the output, positive up here, negative right here, powers up the light. So when I turn on the power, we now have light. But we have what's called pulsating DC, a higher current level. Okay, so the DC is going to be a little bit different than that of a full wave rectifier. Now if I take my oscilloscope probe, I connect one end to the AC power, and I connect the other end to the DC power, we can actually see how some of this output's going to work. One of the circuits that's actually used for diodes is what's called a clamping circuit. This requires a capacitor and a resistor, and the values of both these capacitors and resistors, well, this will determine on how much it is clamped. Clamping circuit is simple. We have an AC signal that rises evenly on the positive and negative side of the sine wave. So if I had something like 30 volts, it would show me about 24 volts on each side. This would be the RMS voltage, root mean squared. Now, once I do the clamping circuit, that's going to take that entire sine wave and move it. So that entire sine wave now oscillates right there on that 24 volt center, from 0 volts to about 60 volts. This is called a clamping circuit. Now, there's also what's called a negative clamping circuit. You still have the same capacitor and resistor as the positive clamping circuit, but now the diode now changes directions. And it does the same thing. Normal AC power coming in. Now the result here is we have a negative voltage coming out. So we can put the entire sine wave on the positive side. We can put the entire sine wave on the negative side. So this type of clamping circuit is used, but it's often found in smaller electronics and a lot of times in security. Transistors. There are 2 basic types of transistors. You can have what's called NPN or PNP. These terms, NPN and PNP, identify how the transistor was actually built. Now, on your drawings, you can identify by the arrow. The arrow going down is NPN, the arrow going up is PNP. So the symbol for a transistor, again, could be virtually anywhere. Most of the time in electronics, but there's a lot of high power transistors used in industry on power circuits, especially in drives. Now, how the transistor is made is by layers of semiconductors referred to as substrates. There's very thin layers that are actually, how can you say, they're vaporized materials, and the materials vaporized are layered upon these things. It's called a substrate. You have a layer of negative material, a layer of positive material, and a layer of negative material. Now, the negative materials right there, you're going to have right there your collector, your emitter, and on the center positive material is going to be your base. The PNP material does it the same way but backwards. You have a layer of positive, a layer of negative, a layer of positive. The leads coming out are going to be again collector and emitter, and the center layer is the base. So these are very thin layers of semiconductor materials that have leads attached to each individual layer. Now, a block diagram explains the operation of a transistor much better. We have the three layers of semiconductors or substrates: collector lead, base lead, emitter lead, all attached. Now, PNP does the same thing. The only difference now is which layer's first, negative or positive. Now, because these are semiconductors, they do not conduct. So if I apply a voltage to them, nothing really happens. How you have this is you've got a layer of negative material, so it has more electrons than protons. So it's negatively charged. You have a layer of positive material which has a lack of electrons. So it has more protons than electrons. And another layer of negative material that has more electrons than protons. These three layers sandwiched together with leads attached. PNP material is the same thing but backwards. Layer of positive, layer of negative, layer of positive. Positive layer has got a lack of electrons. Negative layer has got a surplus of electrons. Now, if I were to take the NPN transistor and I apply a negative 10 volts to the collector, all that negative 10 volts does is increase the negative portion of that semiconductor. It doesn't do anything. But now there is what's called a breakover voltage. A lot of these transistors, diodes, SCRs are going to have a breakover voltage, which is the maximum voltage you can apply. So if I applied 300 volts to this point right there on the negative, okay, let's draw it better. I applied 300 volts right over here going in. That voltage would be high enough to break through that layer. And that current would actually momentary flow, making the transistor explode. So you hear a large pop, a large crack, and nothing works anymore. So to reach a breakover voltage is bad. It destroys the equipment. Now, once I go ahead and take and add a positive voltage to the base, that positive voltage creates a circuit. Now we got a current flow between the 2 points, a current flow between the base. But not only is there current flow, that actually completes the circuit through this circuit, allowing current to flow. So once I break over, get current flowing on that base circuit, that allows current to flow through the entire transistor. So that makes this transistor a switch. If I take the 10 volts away, the transistor shuts off. If I apply the 10 volts back to the base, the transistor turns on. Take the voltage away, it turns off. So this makes the transistor a simple electronic switch. And there's many devices out there that are going to use a transistor specifically for the switching action. This is going to be in your larger equipment, your drives, your PLCs. A lot of standard use industrial equipment will use the transistors as a switch. But there's also another function right here. If I have 10 volts coming in from source A and another 10 volts coming in from source B, what's coming out here on source E is going to be right there on the emitter is going to be about 28 volts. So if I use multiple sources, this transistor creates what's called a gain. So it can step the voltages up. In electronic circuits, that's what a lot of the transistors do on a lot of the circuit boards. Is they're not only used for switching, they're used for the control of the voltage levels. But in industry, most transistors are going to be used for switching action. The PNP transistor is more positive. I apply the positive voltage to the collector, it doesn't do anything. But as soon as I apply the 10 volts to the base, that turns the transistor on, and now the transistor conducts. I take that 10 volts away, transistor shuts off. I apply the negative 10 volts to the base, transistor turns on. So again, we have a switch. We have a switch that can turn on with a positive voltage. We have a switch that can turn on with a negative voltage. But when we start looking at transistors, we're also referring to DC power control. DC. Now, circuits here are simple transistor switching circuits examples. Here we have an NPN transistor. And I'm going to demo this circuit. We have basically, I'm going to show you a 6-volt power source. There's a negative terminal, there's a positive terminal. Well, right now that current's flowing right up there through the collector right there and going nowhere. That positive is connected through the resistor to the anode. But this transistor will not turn on. Now, the positive voltage itself is not only connected to the anode, but it's passing through a resistor to a switch. If I were to close the switch, that puts the positive voltage right there on the base of that transistor. That turns the transistor on, allowing current to flow. The LED in the example turns on. And if I were to open the switch, the circuit turns off. And this is typically how the transistor is used in most industrial equipment. PLC, for example, all sourcing and syncing terminals and cards, those are all transistor controlled. On your variable frequency drive, you got a larger transistor, 2 transistors on each phase to create a synthetic AC power called pulse width modulation. And it's all based on how and when these transistors are turned on. This can be turned on with other circuits. So right here, using an NPN transistor, this circuit can be controlled. So we can control the current flow using transistor as a switch. The NPN transistor, set up just like it is in the PowerPoint, the presentation, there is 6 volts of DC power coming in from a lantern battery. That power passes with a jumper to the collector side of the NPN transistor. From the emitter side of that transistor, that current passes through an LED, through a 330 ohm resistor, and then back to the positive side. Now, the base circuit is sending power through a base circuit, through a switch, through another resistor, 330 ohms, and then back to positive. So as long as that switch is off, that light is off. When I push down this switch to close the circuit, when I apply the voltage to the base, the transistor turns on. So all this transistor is going to be a solid state switch. I apply power to the base, the circuit turns on. I dump the power, the circuit turns off. If I use the PNP transistor on the same circuit, one, I have to reverse the power source, and I have to reverse polarity on the LED. So now we have negative and we have positive. Well, that current right there is flowing up through the resistor to the switch, flowing through the resistor to the LED and the switch both. Nothing happens. And yet the positive terminal is still connected to the batteries. Now, as soon as we close the switch, that puts the negative 6 volts right there on the base of that transistor. When that transistor turns on, that allows current flow in one direction going through that transistor. And if I open up that switch, that drops the circuit out. So again, the transistor can be used as a switch, and it's a normal function in industry. This simple circuit can be duplicated just to understand how it works. Shown on the screen was a circuit for a PNP transistor. The circuit is powered by a 6-volt battery, 6-volt lantern battery. And what I have is a PNP transistor. This little device is my transistor. I have an LED. I have two 330 ohm resistors, and I have a little push button switch. Same circuit is drawn up on the PowerPoint. Now that power, positive side of the battery, is connected directly over here to the collector side of the transistor. The emitter side of the transistor is connected to the LED. The LED passes through, sends power through a 330 ohm resistor, then back to negative. The base circuit takes power right there from the resistor, through the switch, and then to the base. The result is, all I have to do is apply power to the base of the transistor. And once I apply power to the base of the transistor, that turns the transistor on. If I take the power away from the base, the transistor drops out. So all this is showing you that the transistor itself is nothing more than a switch. That's all it is, a switch. It's a solid state switching device. Another circuit that's seen in industry is a circuit that uses two transistors. Here we have NPN and we have PNP. And the idea here is to turn on a load. In this case, again, the load's an LED. Now, here we have two switches. The dotted line identifies an interlock that says both switches operate at the same time. So here we have negative, we have positive. That negative current flows all the way up to the NPN, It passes through and stops. Positive circuit is all the way up through the emitter and stops. That LED is completely de-energized at this point. But now, when this circuit is closed, these switches are closed, that applies a voltage on both of the gates. That allows the current to flow straight through the transistors turn on. If only one switch is closed, the circuit will never work. Both switches are closed is the only way the circuit conducts. Again, this is a very common setup in industry on industrial equipment.